Design of steel structures comprises of design of beams, columns, tension members, compression members, and also the design of connections. In these design methods, we use the elastic analysis also as per IS 800 2007 codal provisions. And now in this video, we are going to learn about the concepts behind plastic analysis and plastic design. Now let's get into it. Before moving on to plastic analysis and design, just click this link here to view this video of summary of IS 800 to get a gist on steel structures by studying the IS 800 codal provisions. Now let's see the first question of plastic analysis. The segment between any two successive plastic hinges is assumed to deform as plastic material, elastic material, rigid material, or non-elastic material. So in this question, we will study about what is a plastic hinge and how it is formed, where it is formed. All those things we will study. Now here they have given the question for segment between plastic hinges. So segment between plastic hinges will be assumed to deform as a rigid material. Now let's see what are the plastic hinges and what are the significance and what are the possible locations plastic hinge can be formed. So first, what is a plastic hinge? It is a yielded zone due to flexure. So here you can see in this example diagram, in this beam, one end is fixed and another end is hinged. And at somewhere between the beam, there is some point load, concentrated load acting over the beam. So here one plastic hinge is formed. At fixed support, one plastic hinge is formed, and here also one plastic hinge is formed. That is here. Here one plastic hinge and here one plastic hinge. So there are two plastic hinges in this scenario. And where are the locations plastic hinges can be formed? These kind of four locations. One is concentrated load. At concentrated load, plastic hinge can be formed on the beam section, and at the ends of member meeting at a connection. So at connection location, there will be formation of plastic hinge, and at points of zero shear, there will be formation of plastic hinge. That will be in case of UDL loading. And at fixed ends, there will be plastic hinge formation. So these are some possible locations where we can expect the plastic hinge formations. So between this section, that is A and B, the beam shall be considered as a rigid one, a rigid beam. So that's why in this question, the segment between any two successive plastic hinges. So here at A, one plastic hinge, and at B, one plastic hinge. Between these two plastic hinges, a segment is there, AB segment. That segment will act as a rigid material. That means it does not have a bending like structure. It just deform like rigid beam or rigid material, because initial slopes and deflections of beam do not affect the virtual work equation. So initial slopes and deflections of beam do not affect the virtual work equations. So we shall see more about virtual work equations in the upcoming questions. Now here in this point, plastic hinges are formed first at the location of greatest deformation. So wherever the greatest deformation happens due to some concentrated load or fixity or something else, then that location a plastic hinge will be formed at firstly, when all the fibers in the section are under yield stress. So this is the criteria for plastic hinge formation at first. And what is MP? That is plastic moment. That is given by MP is equal to Fy into Zp. What is Fy? Yield stress. What is Zp? Plastic section modulus. So what is plastic section modulus and elastic section modulus? We shall see in the upcoming questions. Now let's move on to second one. Which of the following sections has the highest shape factor? Whether it is rectangle or I section or circle or triangle. So shape factor means a ratio of plastic moment to elastic moment, or plastic section modulus to elastic section modulus. So by using that formula, we can find the value of shape factor. So among these four sections, shape of sections, triangle has the maximum highest shape factor. triangle has the highest shape factor. Now let's see other shape factors for other shape. The shape factor shall be given by the ratio of plastic moment to yield moment, or we can say plastic section modulus, that is ZP divided by ZE, elastic section modulus. So shape factor shall be used in the load factor also. Load factor is equal to FOS into shape factor. So what is a load factor? Load factor is nothing but collapse load by working load. Say collapse load is WU. Working load is W. So collapse load by working load gives the value of load factor. And what is factor of safety? That is nothing but yield stress, that is Fy divided by working stress. So these are the some definitions for load factor, factor of safety, and shape factors. These factors are involved in the calculation of plastic design of steel elements. So for I section, shape factor shall be 1.2 to 1.14. So for I section, here you can see 1.12 to 1.14 is the range for shape factor. And for circular hollow section, so here you can see the circular hollow section, it shall be 1.27 or approximated to 1.3. And for rectangular section, it shall be 1.5. And for hatch section, this is the hatch section, it shall be 1.5. What is basically a hatch section? Hatch section is nothing but the I section with weaker axis position. So this is the hatch section. For hatch section, shape factor shall be 1.5, and for circular section, it shall be 1.27, 1.67. Circular section it shall be 1.67, and for diamond, it shall be 2.0, and for triangular section, the maximum one 2.34. That's why we don't usually use the triangular elements or triangular beam or triangular columns, anything, because it has highest shape factor. Highest shape factor refers to highest unused portion of the section. If shape factor is very low, for example, say among these shapes, I section has the lowest shape factor. So that's why I section is used as a beam or column, usually beam for bending applications. What that means, only 12% of the I section is unused or is reserved. For example, in triangular section, it is 2.34. That means 134% is unused. 134% of material is unused for bending or something else, for loading conditions. So that's why triangular sections are avoided in design criteria. Only I section is used as a bending section. So these are some things about the shape factor, load factor, and FOS. Now let's move on to third question. The assumptions in theory of plastic bending are, so there are many assumptions we are assumed we assumed to calculate the plastic design of steel elements. So what are the assumptions? One or many options can be correct. It's a MSQ type question. So accordingly answer it. The first three options are correct. What first option says? The shearing strains are neglected. Yes, shearing strains are neglected in case of theory of plastic bending. Strains are proportional to distance from neutral axis. Stress strain curve, it's idealized to two straight lines. Here you can see one straight line here and one straight line here. So two straight line, we are idealizing the stress strain curve. And fourth option is axial force and shear forces are considered. It is not considered, it is neglected. In plastic bending theory, axial forces and shear forces are neglected. Only bending moments are considered. That is plastic moment, MP, is considered. Stress in any fiber can be found according to its strain. This is based on Hooke's law. Steel is ductile, able to deform plastically without fracture. So steel is assumed to be purely ductile, not a brittle one. So that's why here you can see the straight line after elastic failure, after yielding. Steel is ductile. Strain energy stored due to elastic bending is ignored. So strain energy is also ignored. Axial force, shear force, all three things are ignored. There is an axis of symmetry in cross section. So to avoid twisting over the section, There should be an axis of symmetry in the cross section. Plastic moment is not transmitted through the throughout the length of beam. For example, uh, consider this as a fixed beam, and here one point load is acting, and here one hinge support is there, and if it reaches to collapse load, then deformation shall be like this. Deformation shall be kinda like this. Here one plastic moment and here one plastic moment, and this plastic moment is not transmitted throughout this length of beam section. So that's what it is said there. Plastic moment is not transmitted through. So these are the assumptions regarding theory of plastic bending. Now let's move on to fourth question. Fourth question is based on hinge length. Hinge length of a simply supported rectangular beam subjected to central concentrated load. Like this, central concentrated load. What is the hinge length of a simply supported rectangular beam? So it is L by 3 or L by 2 or L minus 5 or L root 3, where L is the length of beam. So what is the hinge length of the simply supported rectangular beam subjected to central concentrated load? Option A is the correct one. One third of the length of beam is the hinge length. Now we shall see more about it. What is hinge length? The value of moment at sections adjacent to the yield zone for a certain length is more than the yield moment. So this is the certain length they have mentioned theoretically. Certain length is more than the yield moment. So this little length is called as hinge length. And this hinge length depends on the loading type, whether it is UDL or point load, and it also depends on the geometry of cross section. What that means, it depends on the shape factor value. So hinge length depends on two conditions. One is loading condition, one is what type of section, what type of cross section we are using. So for here in this question, they have mentioned as rectangular beam. For simply supported beam with central point load, hinge length shall be given by using this formula. LP is equal to L into 1 minus 1 by S. So what is S? Shape factor. So that's why hinge length depends on geometry of cross section and also the loading type. For central point load, formula goes like this. LP is equal to L into 1 minus L by 1 by S. So if you substitute S as what 3 by 2 for rectangular section, shape factor is 1 by 5, 1.5. So that's why 3 by 2. So S is 3 by 2. That means 1 minus 2 by 3. So 1 minus 2 by 3 goes like 3 minus 2 by 3. So 1 by 3. So that's why L by 3 is the hinge length of a simply supported rectangular beam subjected to concentrated load. So what if simply supported beam subject to UDL? Then formula goes like this: LP is equal to L root of 1 minus 1 by S. Just we have to root over it. Root over 1 minus 1 by S. S is the shape factor. What if in case of cantilever beam? For cantilever beam with point load, it shall be like this formula only. LP is equal to L into 1 minus 1 by S. For cantilever with a point load, the formula goes like this only. For cantilever also, same formula. LP is equal to L into 1 minus 1 by S. So here in this diagram, you can see this plastic moment is adjacent to the yield zone. So these are the yield zones. So this certain length is called as the hinge length. So these are some important points regarding hinge length formation in plastic design. Now let's move on to fifth question. The number of independent mechanisms in a frame is given by small n is equal to capital N plus R. So that means small n is number of independent mechanisms given by small n, and capital N means number of plastic hinges, and small r means degree of indeterminacy or number of redundancies. So option B, n is equal to n into r. Option C and D. What is the correct option for number of independent mechanisms in a frame? So option C is correct regarding this question. Number of independent mechanisms in a frame is given by n is equal to capital N minus r. That is number of plastic hinges minus number of redundancies. So there are four types of mechanisms. One is beam mechanism, one is sway mechanism, one is gavel mechanism, one is combined. Here you can see in this diagram, this is a beam mechanism. What that means, the frame will deform like a beam. So here deformation goes here because here one point load, sorry, here one plastic hinge, and here one plastic hinge, and here one plastic hinge. So this deformation is as like as a beam, and this is called a sway mechanism. The frame is swayed into right side, and this is a combined mechanism. Both sway and beam mechanism is there. So what is the worst condition? We have to find that, and we have to calculate the collapse load accordingly. And this diagram represents the gable mechanism. Gable mechanism. So these are four types of mechanisms happening due to the formation of plastic hinge. So sufficient number of plastic hinges, that is capital N, formed to make structure unstable. So structure will be initially stable and erect while applying load constantly. When that load reaches collapse load, then plastic hinge will be formed, and when sufficient number of plastic hinges are formed, then structure becomes unstable. That structure we call it as a mechanism. Segments between plastic hinges tend to move without any increase of load. So these are the segments. So these are the segments between two plastic hinges. That segment will tend to move without any increase of load. This is also called as the mechanism. For collapse, the number of plastic hinges required shall be R plus 1. What is R? Degree of degree of static indeterminacy, or we can say number of redundancies, R plus 1. That is, in indeterminate structures, insertion of R plastic hinges makes it statically determinate. So that's why plus 1 will cause a collapse, will cause a mechanism. So that's why number of plastic hinges required are R plus 1. And what are the plausible combinations to attain this collapse? Either external work is maximum or internal work is minimum. It is obvious. And the number of plastic hinges is given by ds plus 1, same as r plus 1. R plus 1 is nothing but ds plus 1. ds means degree of static indeterminacy. So how to find the degree of static indeterminacy? Number of reactions minus the equilibrium conditions gives the degree of static indeterminacy value. So this is how we have to calculate plastic hinges, number of plastic hinges, and number of independent mechanisms. Now let's move on to sixth question. For the beams shown below, span AB has plastic moment capacity of MP. So here MP is there. Okay, here MP is there, and span BC 0.9 MP. Here 0.9 MP. That is plastic moment. MP is plastic moment. So what is the correct virtual work equation? So how to find that? So option A, MP theta plus MP into theta plus 2 theta by 3 equal to W2 theta, or option B, or option C, or option G. So just draw the diagram and apply the concept of virtual work equation, that is external work done equal to internal work done. That gives the answer as option C, MP theta plus 0.9 MP into theta plus 2 theta by 3 equal to W2 theta. So now let's see how it is calculated. So first step, we have to identify the number of redundancy or degree of static indeterminacy as 3 minus 2. How 3 minus 2? Here two reactions and here one reactions. There is no lateral load, that's why no horizontal reaction. So here one vertical reaction on one moment, and here roller support, so that's why only one vertical reaction is there. So number of reactions are 3. And how many number of equilibrium equations we have? One is sigma x is equal to 0, that is horizontal. One is sigma y is equal to 0, that is vertical, and sigma m is equal to 0, one is that is moment. Here no uh, horizontal uh, loads, so that's why sigma x is equal to 0 is neglected. So only two equilibrium equations are there, so 3 minus 2 equal to 1. So this is the ds value. And what is the number of plastic hinges? R plus 1. So r is nothing but ds, so 1 plus 1 2. So number of plastic hinges is 2, where one at one concentrated load and at the fixed support. So these are the number of plastic hinges. We can find either by using the concept of plastic hinges formation, there are four possible locations, or we can use this formula to identify number of plastic hinges. And what is the principle of virtual work? It's nothing but external work done equal to internal work done. So here, what is the external work done? Given by this point cloud W, W into del. So this is the del, that is deformation. And how to calculate this deformation? Just multiply length into slope. Here length is 2, slope is theta. Or you can multiply here also. Here 2 theta by 3 into 3. So that gives the answer as 2 theta as the delta value. And what is the internal work done? Internal work done means plastic moment given by the beam material. So here you can see mp into theta, and here also, here you can see here mp into theta it can be there, or 0.9 mp into theta can be there. So whichever is lower we have to adopt that. So that's why 0.9 mp theta and 0.9 mp into 2 theta by 3. So we have already seen a point in the last question whether external work done is more or internal work done is less to collapse the structure. So that's why we are using here 0.9 mp theta uh, at the point load moment. So mp theta plus 0.9 mp theta. So that is here 1 mp theta, here 0.9 mp theta, here 0.9 mp theta, mp into 2 theta by 3. So equating all those things, we will get the answer as this option, mp theta plus 0.9 mp into this theta plus 2 by 3 equal to w2 theta. So this is how we have to proceed with virtual work calculation, principle of virtual work. Now let's move on to seventh question. The distance between plastic neutral axis and elastic neutral axis for the cross section shown below. So there are two things. One is ZT and one is ZP. That is elastic section modulus and plastic section modulus. To find those things, we need the neutral axis respectively. So here in this diagram, we have to find the plastic neutral axis as well as elastic neutral axis and difference between the distance between them. So answer is 26 mm. Let's see how it is calculated. So before moving to calculation, what is neutral axis? What is elastic neutral axis? Elastic neutral axis is the CG axis. That means the axis at which compression is equal to tension. That is the axis at which there is no stresses, there is zero stress. So that is the center of gravity axis. For example, here a neutral axis lies. That is elastic neutral axis, right? The axis at which compression is equal to tension. And what is plastic neutral axis? The axis which divides the total cross section into two equal halves. That's why it is called equal area axis. So let's find first the elastic neutral axis. How to find that? Just multiply, that is a into a1 y1 plus a2 y2 divided by total area. Okay, so what is a1? So this is the first section and this is the second section, that is flange and web section. For flange section, area is 115 to 30. So we have already given here into the y1, that is this one, y1, that is 30 by 2 15. And next web section, for web section area is 115 to 20. And what is the y2 value? 30 plus 150 by 2, 30 plus 150 by 2. We are calculating from the topmost fiber. So that's why it happens like this, 30 plus 150 by 2. That gives the answer as 105 divided by total area of cross section. So that gives the answer for YE as 51 mm. And this is how we have to calculate the YE value. And we are now to calculate the value of plastic neutral axis distance from the top. For that, we have to calculate the total cross section area as, so nothing but 115 to 30 plus 115 to 20. That gives the answer as 7500 mm square as the total cross section area, and dividing the area into two equal halves. So that's why a by 2 as 3750, and calculate the flange area 150 into 30. That gives us the answer for 4500 mm square, and that 4500 is greater than the half of the total cross section area. That means plastic neutral axis lies within the flange. Plastic neutral axis lies within the flange itself. So this is the step-by-step calculation to find the value of YP. So therefore YP from top is easy. 3750 is the half area divided by 150. What so divided by 150 gives the answer as 25 mm. So here we know 3750 is the half area, and breadth into depth, or we can say height, is equal to 3750. So here we know the breadth value as 150. So what is the height from the top to the neutral axis? That is nothing but 3750 by 150. That gives the answer as 25 mm. So these are the steps to calculate YP value. And difference between elastic neutral axis and plastic neutral axis, we have found 51 mm and 25 mm. Difference between them is 26 mm. This is how we have to calculate the neural axis. Now let's move on to 8th question. This question is based on the theorems in plastic design. Here they have mentioned as kinematic theorem. Kinematic theorem has a small factor of safety, whether it is true or false. Kinematic theorem, or we can say upper bound theorem, it has small factor of safety or not. So it is true. Now let's see more about other theorems and also this theorem. First theorem is the static or lower bound theorem. In this theorem, it states that the load actually acting is less than or equal to the ultimate or collapse load, and moment shall be less than or equal to bending moment shall be less than or equal to plastic moment carrying capacity of the beam section, and it is the lower limit to the true ultimate load. That's why it carries maximum factor of safety. This theorem carries the maximum factor of safety, and this theorem is the summation of equilibrium condition and yield condition. So these are 3 points regarding static or lower bound theorem. First one is P is less than or equal to ultimate or collapse load, and next is lower limit, and next is the summation of equilibrium condition and yield condition. And what is kinematic or upper bound theorem? It is somewhat unsafe design theorem, and it says load acting shall be greater than or equal to collapse load, and this is the upper limit to the true ultimate load, and it has the smallest FOS, and equilibrium condition plus mechanism is the uh, kinematic theorem. So kinematic theorem gives the summation of equilibrium and mechanism. So what is mechanism? It is a collapse condition. What is yielding? Yielding is something related to working. So kinematic theorem is unsafe. And there is another theorem called uniqueness theorem. Here they have equated all those things. External load is equal to the collapse load, and bending moment shall be equal to the plastic moment carrying capacity. And here all three things are summed up: equilibrium plus yield condition plus mechanism. So these three theorems are important regarding plastic design, and upper bound theorem is unsafe and lower bound theorem is safe. Now let's move to ninth question. Which of the following statements are correct regarding plastic design? Structure designed by plastic method is economical. Plastic method produces an optimum section in a single attempt. FOS is same, that is factor of safety is same in both plastic and elastic design of indeterminate structure. For indeterminate and complicated structures, the plastic method is more conveniently applicable. So here more than one options are correct. So what are the statements that are correct regarding plastic design? Plastic design in comparing to elastic design. So all the 4 options are correct regarding plastic design. First one is structure designed by plastic method is economical. That is, it saves around 10 to 11% of material when we use plastic method over elastic method. Plastic method produces an optimum section in a single attempt. There will be no extra trials to make a design. If you see in IS 800 portal provisions, there are some trials and there are many trials to make a design. But here in this plastic design, we use only the plastic moment carrying capacity and the virtual work method to obtain optimum section. And factor of safety is same in both the cases, but the factor of safety given by plastic design is reliable, somewhat reliable when compared to elastic design. And option D is for indeterminate and complicated structures, the plastic method is more conveniently applicable when comparing to elastic design. Another some points are stresses produced by settlement, erection, etc. can be determined more correctly by the plastic method. So stress produced by settlement, foundation, erection. So these stresses can be more conveniently found by plastic method based on plastic deformations produced by hinge mechanisms. The saving in steel is about 10 to 15%. That's why it is economical. Now let's move on to now let's see the 10th last question. Collapse load for a fixed beam subjected to UDL is given by W is equal to 8 MP by L, W is equal to 16 MP by L square, WU is equal to 2 MP by L square, WU is equal to 4 MP by L. So how collapse load is given when a fixed beam subjected to uniformly distributed load? Option B, WU is equal to, that is collapse load is equal to 16 MP by L square. Now we shall see more other collapse load. These are some basic structure. For simply supported beam subjected to concentrated load at center, WU is equal to 8 MP by L. For a fixed beam subjected to concentrated load, W is equal to again 8 MP by L. Both are same. For a beam like one end is fixed, another end is hinged and subjected to UDL, then W is equal to 8 MP by L square. For a fixed beam subjected to UDL, in this case, in this question they have given 16 MP by L square. And for this case, UDL is somewhere between a simply supported beam, then MP by L by AB, MPL by AB. So these are some important formulas for a standard formations. Here you can see one important formula, that is a beam having one end fixed and one end hinged, and also a uh, plastic hinge at 0.414 L from the hinged support. Then what is the collapse load? W is equal to 11.656 MP by L square. So plastic hinge will happen at 0.414 L from the what hinged support. So these are some regular or basic arrangements to find the collapse load. How collapse load is found? By using principle of virtual work method. So this is how we have to calculate the collapse load. So now we are at the end of this video. So we have covered all the important concepts behind plastic design of steel structures. If you like this video, please like, comment, share with your friends. Thank you for watching.